So today is, I guess, the second last, well, this is really the last real sort of review-y type thing for many of the stats course you've taken. Okay, or refresher if you want to say that. So today I'm going to call it t-tests, which I've for some reason used lowercase letters because it's hip and cool or something. I don't know why I did that. I don't know. So let's talk a bit about these. You know that, like when I came in, that second from that's pretty cool, right? So to find the probability of a given value of a variable, assuming the variable is normal, we convert it to z-score and we look it up in a table. Right? Z equals x minus mu over sigma. In other words, we convert it to standard deviation units and we look it up. Right? Talked about that last time. It's something you've done before. And as I said, it's also, the other day, it's also something you normally don't do. That's not a thing for just individual values. It's usually for means, right? Which is what we're going to talk about. So that's how you do this. You look it up in a table. We usually deal with means, not individual values. In fact, I don't know that I've ever seen anyone find the probability of an individual value in a paper. I've seen people use box plots more often in papers, more often than I've seen someone say the likelihood of this individual score. That's just not something that comes up. The reason you have to know it is it's the basis for everything we're free to talk about in the course. But no one really does this as an end into itself. Okay? All right. We usually care about the distribution, not of x, but of x bar. We don't care about how likely a score is, we care about how likely a mean is. Okay. And remember, when I talked about hypothesis testing, I said, how likely is it that these two means come from a distribution that looks like this? So we care about means. We don't care about individual scores really exhibit. There are cases where we might do something like to include certain people in a study. Let's say you're doing a study of people with really high IQs. So immediately Dupuy is out. Right? Joke. Paul Dupuy humor. But let's say you say, okay, I want people that are above 150 IQ points. Or, and the probability of that is whatever it is. Right?
That's pretty funny, man. Honestly.
It's like 0.999 something. I thought it was pretty funny, man. So yeah, cool. You might do it that way to exclude people or include people in a study, or rats or plants. If you're Brandon Shampling, you're boring. I study plants. My name's Brandon. He's my friend, but I make fun of my friends. I like calling him a gardener, a glorified gardener. It's fun. I get a real kick out of that. I don't think he does, but it's the point. So, we're going to care about the distribution of x bar. How likely is this mean to have happened? This goes back to it. I mentioned central limit theorem last time, but I didn't actually have it written out for you. This is the central limit theorem. This is what I want you to know word for word. There are very few times in my life, in my career, in what I do, when I say you have to know exactly what I am just right there. Given a population of mean mu and a variance sigma squared, the sampling distribution of the mean, mu sub x bar, equals mu, and a variance of sigma squared over n. As it increases, this distribution approaches normal no matter what the shape of the parent population distribution. So if on the test next Thursday, when it's an open book test, and the thing says central limit theorem, write that down. Here's a free point. If it's on the quiz on Tuesday, memorize that. I don't ask that often for you to memorize things. In fact, I've taught most of you before, I think. I don't ask you to memorize things typically. Sometimes I'll list, here's the 7 steps and nervous transmission. A few things in 26 and 6, I guess. But typically that's not my scene. But this is important. And it's not, because it's a theorem, mathematical theorem, the words matter. The words matter. There's also a proof to this, and I'm not going to show it to you, because A, I don't know it offhand, B, it's not going to help us. If you want it, go look it up and you can figure it out yourself. This just is true. Okay? There is a proof, but I haven't seen the proof in 30 odd years. I have a book that has the proof in it in my office. I think it's in my office, it might be at home. Yes, on my night table beside my bed, I have 3 statistics books. That's how exciting a life I lead. And I actually do. Including my second-year stats book that I still use to this day. Okay, given a population with a mean mu and a variance sigma squared, all that says is we have a population of something, we don't even know what the variable is here. Doesn't care. The numbers don't know where they came from. But we can say it has a mean mu and it has a variance of sigma squared. Notice I didn't say anything about the shape. I just said we have a distribution. And it has a variance of sigma squared, and it has to be a non-zero variance. Well, it has to be non-zero because it's a variable. If it has a zero variance, it's a constant, right? It would be all the same number all the time. Yeah. Good. So, the sampling distribution of the mean, what does that mean? That means if I took an infinite number of samples of a given size and then plotted out all those values of that sample mean, of those means, I would get a distribution of means. Does that make sense? It's good, right? Okay. The mean will be the same as the actual mean, mu sub x bar, the average. Whoa. The average will be the same as the average. And it'll have a variance of sigma squared divided by n. So as n increases, that means the sampling distribution of the mean's variance will get tighter. The cool thing also here is that it'll be normal. No matter what the shape of the parent population distribution. The parent population distribution could have literally 2 values if you were going to normal distribution for the sampling distribution of the mean. And as I said the other day, you can try it yourself if you feel like it by flipping a coin 5 times and counting, we'll get heads a score of 1 and tails a score of 0. Do it, flip it 5 times, what was the number you got? Then do it again and again and again, and do it 30 times, and plot it out. You'll be amazed. You really will get a normal distribution. It's kind of weird and cool, because this sounds kind of counterintuitive at first, but then when you actually do it yourself, or roll a die 5 times and just say what the average die roll was, then do it again, and do that 15 times. Or if you're halfway decent at writing a computer program, you can probably do this in about 5 lines of code. If you're not a person who does that. You probably Excel to do it. Generate random numbers, yeah, you can. Anyway, it doesn't matter. You'll get this normal distribution. It's very cool. You hear a lot of people say it has to be about, it has to be about 30. It has to be about 5. It works out about 5. And it actually works, well, if you did it an infinite number of times, it works at 2. And at 2, you have to do a lot of samples, that's all. So people talk about the magic of 30. That's the law of large numbers. That's not related to the central limit theorem. They confuse the two law of numbers. Some stats books confuse the two, which makes me sad. People have said to me, Dave, why don't you write your own stats book? And I've said, that smacks of effort. I have a job. Also, I don't want to write a book. Plus, the book we have here, Gold Standard, is the book for this course, I think, anyway. All right, questions? Okay. As much as that's sort of sarcastic, saying, ooh, the power, it's actually also true. I feel that this is really neat because I don't have to know anything, and I can talk about it as a population. So the population distribution shape doesn't matter. What matters is random sampling. This is assuming a random sample. It matters a lot less than you might think. Because you might say, wait, I see all those people talk about their psychology honors thesis pair projects. or their biology honors business projects. And they're doing statistics. And are any of them actually randomly sampling the population? The answer, of course, is not a chance in hell. We don't have the money to do a random sample, or the time. And it's the same thing with the biology ones. You thought it could be, songbirds, Jen Foot. It could be something to do with plant growth, Brandon Chen. It could be anything, right? And comparing that to heights and days. Brandon actually is really cool. I like to make fun of him. It's really cool. But nobody's randomly sampling anything. And it's not just because we don't have the money because we're a small school. Nobody has the money to do that to do a random sample. Wait a sec, but then how does all the science work? In things like in hard sciences. When I say hard, I mean difficult, like biology and psychology, not easy ones like chemistry and physics. We're dealing with complicated living organisms. Yeah. You know why we don't have to randomly sample? It hardly matters at all. It matters, the math it rests on it matters, but when you simulate doing samples and you don't use random samples, it works almost perfectly. So close to perfectly that it just doesn't matter. Which is great. So it's a wonderful thing, actually. So it doesn't really matter that we don't have random samples. Yay. I mean, please. So to find the probability of X bar, and that's what we're interested in, how likely a mean is, we have to just use our old friend, the Z-score. We just use the Z-score. But we're going to do it a little bit differently. We're going to find out how likely a mean is in a distribution of means. And as odd as that sounds, the numbers don't know where they came from. And we know it's going to be normal because the central limit theorem told us so. So this is mathematically completely cool. There's no issue doing this at all. So this changes things a bit. So now we go from Z equals a score minus a mean divided by the standard deviation. Well, the score is now a mean. Right? The population mean is actually the same because the central limit theorem told us. The standard deviation of the sampling distribution, the mean is, it's sigma over root n. The central limit theorem told us that. It just is. So we may have thought when you took an intro stats course that this was a different formula, you had to learn a brand new formula, and you wrote down on your little cheat sheet, you get a little formula sheet in that class, in the intro stats class, you get a little formula sheet, right? And you make up your own little formula sheet. Oh yeah, that's what typically people do. And a lot of you wrote things like for a mean, for a score. Actually, if you know the central limit theorem, you didn't even have to write this one down because you just know this. A friend of mine used to make the cheat sheets up, the formula sheets up for classes. They could use his formula sheet. But he would put on formulas, but he wouldn't say what they were for. He also put on formulas that had nothing to do with statistics. Like he put on things like you just write down 6.02 times 10 to the 24th. Just have a guy knows number on it. Put on like Charles Law and Boyle's Law. So my friend was kind of a goofball that way. In a good way. I kind of enjoyed that. When I was in my stats class, they would only give you half the formula. They'd only give you the right half. So you'd get x minus b over sigma. You wouldn't get z equals. And I learned very quickly that I didn't need to have that because I just studied. Makes you feel good to have it, right? Didn't you find out when you took those courses, like intro stats kind of classes, the first time you're looking at it, the second time it's like, I don't really need this. I don't need this. This just makes you feel good. The best thing is, when I used to do it, when I used to do this course before I started saying, oh, screw it, just use your books. I used to approve people's formula sheets. I was amazed at how tiny your writing can get when you want to have it on one page. It's like you should be monks doing things for calligraphy, which was impressive. And always the one guy that just comes in and he's just got written on the back of an envelope. I don't know, it's this. Okay, that's fine. Anyway, this and this are they're equivalent. It's just that we know that x becomes x bar, sigma over root n. Questions? Here's an example. So let's say with 25 subjects, I guess we have to call them participants now. When that changeover happened, it was in the late 90s, so I mean, I'm obviously a dinosaur. But when that happened, I actually got a thing back from an editor saying I couldn't call the pigeons in my paper subjects. I had to call them participants. And I said they hadn't signed a consent form. These were subjects, not participants. I'm going to call them animals. How's that? Anyway, 25 subjects are given an IQ improvement course, which, as an aside, would not work. And then our IQ is tested after the course data with an IQ, mean IQ of 110. Mean IQ of 110. All right. So IQ population is a mean of 100, a standard deviation of 15. As I said the other day, the reason we use IQ all the time is we actually know the value for sigma in the population. So that's why we use that. That's why it's used as a running set of examples in stats courses, because we actually know the sigma of the population. And almost every other variable in the world we know. Okay. So Z equals X bar minus B over sigma divided by root n, 110 minus 100, 15 over root 25, n is the number of subjects, number of observations. Or if you want to use fancy stats words, the number of experimental units. Z equals 10 over 15, divided by 5, Z equals 10 over 3, Z is 3.33. The probability then of getting a Z score, of getting that mean with that many subjects is vanishingly small, actually. The probability is less than 0.00043. So my old calculator told me. In fact, that value is so big that if you have a Z table at the back of your book, which you know you do, it doesn't go up that high. It's virtually impossible to get that by random chance alone. It could happen. There's, 43 100,000ths of a chance it would happen. It's not random chance. So that's how you do this if you do the population variance, right? That's how you do one of these kind of things. And again, I know that you've all done these. You may have forgotten doing them. Maybe having flashbacks to doing them. There's a real issue there, though. And that's that we typically don't know sigma for a population. It's just not something we know. You can usually either know mu for a population, or you can think of some theoretical value it could be. For sigma, you can't. It's just not a thing. We use IQ because we actually do know it that way because the tests are designed to have a mean of standard deviation of 15. Well, wait a second. The expected value of S squared is sigma squared, right? Right? It's an unbiased estimator. Okay. Well, if that's the case, why don't we just sub S squared in for sigma squared? Yeah, that's what we're going to do. But now we have two sampling distributions to worry about. We have to worry about the sampling distribution of the mean and the sampling distribution of the variance. Oh, yeah. Two things to worry about. And the sampling distribution of S squared will change depending upon the variance because, as you know, just look at the formula. X minus X bar squared over n minus 1, right? That's what S squared is. Okay, so it gets smaller as n gets bigger. We have to take this into account. We can't just use S squared, we have to take into account the number of observations. Okay. Questions so far? You have any questions for me? Yes, please.
Will you give us the value of mu on a test?
Well, you have to figure it out. Yeah. But I mean, if I give you a batch of numbers, say I give you a batch of 8 numbers, 10 numbers, you should be able to figure out the mean pretty easily. You got a calculator in front of you, right? Now, if you need to figure out mu, it'll either it would be obvious. Or I'll directly tell you. Oh yeah. So we can't use Z. So we use something called T. T was developed by a guy named Gossett, and he worked at Guinness brewery. Okay. But he couldn't. Guinness liked their scientists publishing. They thought it's great. But they're like, we don't want you publishing under your real name because we don't want people to steal you. We don't want people to poach you. So he published under the name Student. Like he was a student, which is great. That's why it's sometimes called Student's T-Test. Even though his name's actually Gossett. But imagine being a statistician in a brewery. It's like my dream job. So, where do we get that formula? Well, it's basically the same as the T formula. We just put S in where sigma was. Same as the Z formula. All right. T changes depending on the number of observations. Because S squared changes depending on the number of observations. Okay? And in fact, it changes based on the degrees of freedom to estimate sigma squared, or by calculating S squared. We had to fix a value, that's the mean, the calculated, to calculate S squared. Remember we talked about degrees of freedom the other day. As the freedom the numbers have to vary, that's degrees of freedom are, or the number of values that can be arbitrarily assigned. Right? This is actually really a really powerful technique, because now we don't have to know anything. We don't have to know the shape of the parent population distribution. We don't have to know the variance. We have to know the mean in the population, but you know what? That's kind of almost like a gimme. It's almost always there. So we have to hardly know anything about the population. We just have to know about our sample. Okay? Questions? Right? You've done this. You've played the t-test before. Okay. So if we have pairs of observations, things change a little bit. It's the same damn formula. So, and these are pairs of observations. Let's just, you like that? Pretty cool, right? So, X bar sub D, S sub D, and N. Now, N is the number of pairs of observations, and S sub D and X bar D are the difference scores. So if we have pairs of observations, let's say we would, well, what about just using the same people as their own control kind of thing? So before and after. So instead of our IQ improvement course example, and when you think about it, that's a kind of funny example because we didn't give them a test beforehand. We just assumed before when we calculate their IQ, that on average it would be 100, right? But we didn't do before and after. If we did before and after with this, we measure people's IQs before, and then after the quote IQ improvement course, give them the same thing again, and then subtract after, or sort of before from after. And what's the expected value if there's no effect of before minus after? 0. So really it's X bar sub D minus mu. You know what mu is? It's 0. So we just don't put it in the formula. It's 0. And again, you likely thought this was an entirely different formula for a t-test. It's not. It's the same damn formula. It's just that we used, this is minus 0. Minus 0 you can take off. You can remove it.
Sorry, I feel like some professors, some people actually like ask us to keep the 0?
Some might.
Okay.
I think they're overthinking things.
Okay.
Because they may be doing that for a pedagogical reason, and that is, you should remember that that's actually there. The mean difference should be 0. But when would the mean difference for a null hypothesis ever not be 0? Except in a statistics homework. That would never happen. Like, it just wouldn't be a thing. So typically, you just think of the formula like this. If you really want to have the whole damn thing, sure, -0, it's true. And then you do see again, usually in homework problems at the end of the chapter about t-tests, it'll say, it's assumed that the difference between the two groups will be 5. No one does that. It doesn't happen. Right? So it could be pairs of observations, say person. It could be matched pairs. So let's say we're doing a blood pressure group. So we want to match subjects on their blood pressure. Okay. So we put everything together, measure their blood pressure, and it turns out that me and Matthew were almost exactly the same blood pressure, which is exceedingly low. I think I'm much more hard strung than you are. But anyway, so we're now a pair. And you guys are a pair, you're a pair, etc. Okay? So we do that, and then if there's no difference, I'm taking the medication and you're not. If the drug has no effect, we're fine. We have, there should be no difference. We still consider the difference to be 0. It should be 0, right? So you can do, that's what's called matched pairs. That's a thing you can do. So sometimes it's called a matched pairs t-test. Sometimes it's called a correlated t-test. So matched pairs of observations on the same person or same subject and same rat. Or you could match pairs. Okay? Now you gotta be pretty careful here because typically how do we assign subjects to conditions? We do that by randomly assigning them. Because that's the best way to make sure that by, dumb luck, they're basically the same. What you've done here is you've made sure they're the same on one variable and completely different on everything else. Right? So this better be a damned important variable. So we better have determined that if we're doing our blood pressure thing, that age is unimportant here. Because I don't know how old Matt is, but he's not 54. And I am. I'm old. Please help me. When you start doing things like, I'm going to retire in like 11 years, it's like, what? I still feel like I'm 12. And I literally had the same clipping as I had when I was 12. Same likes and dislikes, except for the alcohol and the weed. But everything else is the same. Like I like the same hockey team. I like the same things like video games. Or like I'm literally thinking what I'm going to do in my next move in a game of Civilization as I'm talking. So frightened of women. Like it's exactly the same. And men. Really people. I don't like people generally. Except for you guys are awesome. Everybody else. Nobody in the hall, which is good because I can't stand them. Okay. So, better be that blood pressure is really important here. Because everything else, the two of us, is pretty different. Though his grandparents live next to me, which is weird. It's a little weird, it's a small town, I'm just saying. So, we're great people. You can even pressure your grandma. Does a lot of that, doesn't it? It's funny. Yeah. Anyway, we can do a whole thing about it. None of you else will get the joke. But anyway. What if your pairs aren't matched, which is usually what we have? Usually we've assigned subjects to groups. And pretend we assign randomly everybody on this side of the room to a group. We have randomly assigned this side of the group. And you know from research methods courses why we randomly assign, because we can't measure all variables and make sure the groups are the same. What we can do is randomness can be our friend and we randomly assign subjects to groups. Great! Maybe they come from two populations. Maybe. I Our null hypothesis is they don't, but maybe they do. Right? So our hypotheses are like this. Whole is mu1 is equal to mu2. Mu2, of course, are my favorite band. If you've been in my office, actually, it is mostly a shrine to mu2, but that's beside the point. U2 are great. Mu2 are just average. That's a statistics to average joke. Funny. There are no funny stats jokes. HO is that mu1 equals mu2. In other words, the two, they're same population. HA or HA is that mu1 is not equal to mu2. We could put a direction on that. mu1 is bigger than mu2. mu1 is less than mu2. Let's just say it's not the same. Okay. So before it was that the two means, I should actually throw them in there, that for the matched, excuse me, for the matched pairs t-test, it's that mu1 minus mu0, we call it that, equals 0, and the HA would be mu1 minus mu0 is not equal to 0. Right, this is before and after 1 and 0. Or even 1 and 2 is right now. Okay. So the original T formula looks like this. T equals x bar minus b divided by s over root n. I don't know how times I've said that in my life. It's a big number. I have a pile of nickels if I was given a nickel for each time. And remember, this is the statistic we're interested in, x bar. That's the HO, mu. And that, of course, is our spread outedness, or we will call it our error. And in fact, S divided by square root of n is called the standard error. Or the standard error of the mean. Okay? So we need statistic minus HO divided by standard error of the mean. That's what we need to figure out for two groups. For two groups, Mr. Spock. Sometimes I find myself becoming William Shatner. It's really weird. So, x bar 1 minus x bar 2 is our statistics we're dealing with, because we have two means now, your mean and your mean. And we're going to subtract what our null hypothesis is, mu1 minus mu2. And practically, and we're going to divide by error. We're going to work on that yet. But practically, the mu1 minus mu2 should be 0. So let's just leave it at 0. And again, maybe you were taught that you should always have that there too, but it really is just 0. So practically, it's 0. Because our null says that mu1 minus mu2 is 0, or mu1 equals mu2. So why put it in? So the t is going to be x bar 1 minus x bar 2 divided by some estimate of the error. But the error thing's weird here because it's of two potentially different distributions, two sampling distributions. We've got your mean and your standard deviation, and your mean and your standard deviation. So we're estimating using two different quantities. So to put those together. I mean, I know you know where this is going, but. And the error is weird. The variances have to be weighted somehow. So if we have different numbers of observations per group, which do we actually know? It's almost saying 1, 2, 3, 4, 5, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. We literally had exactly the same number of people in each other group. Wow. Well, let's pretend I'm in this group. Now we get 10 over here. We're going to kick you in the ass. But I don't know what this is at. Halo. Bring my son in and pull us all. In Halo, he's not a murderer. He's a tough kid, but he's a giant of a man, actually. Anyway, we would want to weight this because our variance here is calculated based on 10 people, and your variance there is calculated based on 9 piddly people that can't beat us at anything. Football, baseball, hockey, well, what do you compete? Running, you're screwed at 54 years old. You're screwed. All right. So we're going to take each sample standard deviation, divide by number of observations. That'll standardize it. Right? Because ours is based on 10, yours is based on 9. You guys are actually probably better than us, but I'm feeling insecure, so I'm going to trash talk you guys. As long as it's not Scrabble, you get a chance. I am horrible at Scrabble because I have no patience. And I just I don't sit there and look for a good word and go, oh, good, cat, we'll just put that down. And meanwhile, what I had, I could have used, I also had category, but it's like, no, screw it, cat, next. I have no patience for Scrabble. My wife, who it's even her first language, she didn't speak English till she was 18, kicks the shit out of me in that game. After that, I was saying, want to go play some video games? Go play something where I'm going? But she's also smarter than me, probably, so she's a better writer than I am, too. And again, it's not her first language. I suck. So for our error, what we got to do is it looks like this. So, because that was variances, we're going to take the square root. So we're going to do x bar 1 minus x bar 2 divided by s squared sub 1 over n sub 1 plus s squared sub 2 over n sub 2. I have 2, yes, square that whole quantity. So it's always the same formula. We're just subbing in different things. It's statistic minus null hypothesis over standard error. Now, there's something that's going on here which is, because I know you know there's another way to do this. This assumes the variances of our two groups are equal. And actually,
Does it matter which one you subtract first? Because x2 minus x doesn't matter if you x1 minus x2 or x2 minus x1.
because it might come out negative. I usually put the higher one first because I don't know why. But t can be negative. It's a symmetrical distribution of t distribution, so it can be negative is our problem.
And the same at the bottom doesn't matter.
Doesn't matter. No, doesn't matter. That's a good question. A lot of times people will tell you to put the bigger one first, but it really doesn't matter. That's because their t distribution t-table doesn't have negative values and confuses people, but if you realize that it's a symmetrical distribution, so the negative probability is the same as the positive probability, it doesn't matter.
So if you're taking square root of a negative number, that doesn't work.
Oh, it's not going to be a negative number, because you're adding.
Oh, okay.
You're adding, not subtracting. And this is something, thanks for pointing that out. So Alan makes an interesting point, because a subtle thing that I forgot to mention. Even though we're subtracting both of them, we can't subtract variances. The variances have to add together. Variances always add. When you take two distributions and put them together, okay, you add the variances. It's just a thing. Okay? You say, yeah, you're subtracting. Well, subtracting is just the negating the addition. So it really is the same as addition. That's it. Thanks for mentioning it. Okay. Two good questions. Now, this assumes the variances are the same. As I said, the problem here is that we don't really know the variances are the same, do we? We can't know that. If we knew that, we wouldn't really have to do the science because we actually know in advance variances. That's not a big deal. It's, if one is maybe twice as big as the other one, you can use that formula. That's a good rule of thumb. You can also test, you can do a statistical test on the variances to see if they're significantly different, if you want to. Or you can be kind of safe and use something where instead of using both variances on their own, you pool them